Welcome everybody to the Spring 2002 lecture series of the School of Architecture and Design at the New York Institute of Technology. I'm Alessandro Melis, the chair of the Lectures and Events Committee, and would like to welcome everybody on behalf of our Dean, Maria Perbellini. The topic of our lecture series this year is communities, and we intend this as communities beyond borders. We think this is particularly important these days. And this will offer us opportunity to discuss and debate how the application of architecture, design, digital arts, and urbanism in this context can achieve positive impact, innovate, and be of benefit to communities and society. I wish today to particularly thank Pablo Eiroa for having conceived and curated this event within the context of the Master Architecture and Computational Technology, which addresses the theme of communities through a very original and highly significant perspective from my point of view, due to its implication between advanced technology and post-Fordist societies. I also want to take the chance to thank Sandra Manninger for her contribution and our distinguished guests for being here with us very generously today. The stage is yours, Pablo. Thank you for your generosity in organizing this event.
Thanks, Alessandro, and welcome to today's lecture hosted by our new MS program in Architecture Computational Technologies at New York Tech. I'm Pablo Lorenzo Eiroa. I'm the director of the new program, and I would like to introduce today's event with my colleague Sandra Manninger, who's also teaching in our new MS program. Today's event is entitled Automation in Development Through Collectives. And it's a difficult topic, so hopefully we're going to be able to frame it and be able to construct a relevant discussion in relationship to what's going on today related to automation and post-Fordist society, as Alessandro mentioned. Architecture has been often related with construction, development, and growth. Its socialist version is often identified with developmentalism, while its capitalist version is often identified with object-oriented construction. Architecture's most ecological version has been often identified with recyclable materials, net zero positive energy production, but mostly about adding to the built environment. In urban terms, socialism identifies a relationship between class struggle, labor, and production. The urbanism of capitalism identifies the city as business and economic growth through real estate speculation. Urbanism's most ecological version could be identified with circular economy and ecological inference. But these topics seem to offer limited ranges of possibilities that are not correlational with the set of crises we're facing, nor the horizon of what is possible. How can architecture activate notions of void against notions of built environments? Architecture can be thought as reading, understanding, and deviating environmental forces, expanding relationship between spaces and environments. Architecture can be thought as activating voids, recycling existing built environments, and activate latent ecologies rather than adding to the built environment. How can architecture construction or deconstruction be thought altogether in relationship to the energy and social crises that we are facing? How can architecture be thought in terms of the environmental evolutionary logic, such as environmental processes for passive energy and gross healing for materials? How can architecture be thought as minimal interventions in relationship to maximum possible social and ecological commons? How can automation, innovation, decentralization, and community emancipation be understood in relationship to current technologies, such as blockchain, automation, simulation, and robotic construction, or even deconstruction? The event will discuss the work of radical, innovative architects in which environmental, economic, and social communities issues are related to notions of automated construction, devising notions to expand possible commons. Thank you for joining us, and now I will give the word to my colleague Sandra Manninger, who's also collaborating in this event and is also participating in the moderation.
Thank you so much, Pablo, and welcome everybody. I'm Sandra Manninger, and I will proceed to introduce today's speakers. We have Maida Giugano Monica, assistant professor at Université Catholique de Louvain. She will be talking about site surveying. We have Evangelos Panatasis, computational design lead at IBI Group. He will discuss how to manage complexities in historic designing behaviors. And then we have Dr. Hannah Dahi, Biomed Director at the Institute of Building Structures and Structural Design, University of Stuttgart. She will introduce natural smartness, a new era in sustainability. And finally, Neil Leach, Director of the Doctor of Design program at Florida International University, will give a presentation on architecture's Sputnik moment.
Thank
Maida,
you, Sandra.
the stage is yours.
I'm going to introduce Maida. Maida is going to be talking about site surveying. Considering both a science and an art, site surveying has become one of the most fascinating and she would argue most important task in the architectural and urban design processes. This is particularly the case in current times when the questions of urban ecology are central to our agendas and designers. Recent studies have revealed the strong interurban environmental gradients that characterize cities with up to 8 times worse concentration levels within an urban block distance. The death rates from the SARS-CoV-19 virus has been also shown disconcerting spatial patterns, evidencing the strong socioeconomic and environmental inequality present in cities. That is, without a detailed SARS survey, we won't be able to identify the local environmental pollution sources, topography, and flooding risk, or the urban comfort conditions, amongst others. Maider Laguna Muchinta is an architect, co-director of ACPML, an assistant professor at UC Louvain. Maider obtained her PhD from ETH Zurich Institute of Technology in Architecture in 2016. Her research topic focused on the study of architectural and urban design strategies to modulate the urban environment, its microclimate and air quality. Prior to her PhD studies in 2010, Maider graduated with Excellence in Design honors from the GSAPP at Columbia University. Maider obtained her diploma in architecture from the ETSAB with honors in 2006. Prior to joining UC Louvain, from January 2017 until August 2020, was an associate research scholar and postdoctoral research at the Department of Civil and Environmental Engineering at Princeton University. From August 2020 to January 2021, Maider was assistant professor at the School of Architecture, CAMD, at Northeastern University in Boston. Maider's work has recently been awarded with the 2019 London Hindenburg Beyond Bauhaus Prototyping the Future Award and the Columbia University GSAPP Incubator Prize Award, amongst others. Thank you for joining us and welcome, Maider.
Thank you very much for the introduction, Pablo and Sandra. So I'm going to start sharing this, my screen now. All working well? Can you see my screen? Right. Yeah. So I'm super excited to be here, first of all, with such a fascinating crowd. So thank you very much for the invitation. As Pablo and Sandra mentioned, my topic of presentation today will be site surveying. And as we know, site surveying also means gathering information of the sites, right? Measuring and documenting the existing conditions of the site, which dates back to Egyptians who made use of measuring ropes to gauge the dimensions of various land plots. And we make a big jump in time to the 16th century. I'm showing here the treatise Antometria, written by Leonard Digges, an English mathematician and surveyor who is also credited with the invention of the theodolite, which is an instrument that transformed completely the site surveying practices, especially so in the late 18th century or the turn of the 19th century, with work of geographers such as that of George Everest, which we all know. And of course, also especially so where I am virtually today, Ferdinand Hassler, who documented the coastline in the New York area, right? And here we see one of his illustrations. But I also wanted to highlight really what he meant back then to do site surveying, right? These were instruments that were very hard to acquire, very heavy. We see the effort it meant moving around one of these over 300-pound boxes to the experimental sites, no? And especially so for the case of Hassan, who reportedly died out of injuries that were caused while protecting the instruments in one of these experimental campaigns, right? It was a really involved process, which is very different to what is happening today. Now we have access to many tools, and this has become sort of affordable and accessible also for architectural students. Here I'm just showing some examples of student surveying approaches, and one of them related to Neil, that's why I'm bringing it along. But we can do, through the use of drones, we can scan large areas affordably. We can collect many images, we can do sensing with local sensing technologies. We can do also LiDAR scanning in kind of an affordable fashion, which is really transforming the way we can work with site conditions in architecture. No? We can understand the physical environment to higher and higher spatial temporal resolutions. And I think this is something that is going to become increasingly crucial, especially so in current times, when we really need to address the contemporary ecological challenges, no? And especially so those challenges related to urban health. And for that, amongst other things, we need to have this kind of detailed understanding of the site conditions to be able to do a life cycle and environmental assessment of these sites. And it is through the use of these technologies, for example, sensing technologies, that we are gathering the evidence to understand the environmental inequality that is present in cities, for example. And this is, of course, very important to be able to address these critical challenges also from the discipline. So the message that I wanted to put forward today is that urban environmental surveying approaches are to be developed to understand to high spatial temporal resolutions the local specificities, and here I mean from geometry, materiality, the topography, buildings, and so on. Also the subsoil conditions that we can access increasingly accessibly, and local environmental gradients from air, thermal, noise, and so on. And of course, the ambition being to inform, finally, local architectural, urban design, and planning strategies to improve urban health. So I'm going to be very briefly presenting 3 research projects that are going to be zooming in a scale. So the first one is operating at the city scale, so city scale environmental surveying, making use of readily available data. And I'm going to be showing 2 cities, New York City and LA, because are closest to you. The way this kind of data-driven approach works, the ambition is always to collect environmental data and related data that is going to be affecting environmental gradients, and develop a model to be able to predict the environmental parameters at the sites we don't have data for, right? Because sensors are limited in cities. So we have to kind of model the remaining urban sites to be able to acquire data for those as well. So for these 2 cities, for example, I collected data for the environmental data again through direct sensing and remote sensing sources, then building usage data, urban design data, and socioeconomic data. And then, of course, there is a long process of data formatting, because each data source is different. And then the development of the data analysis and model preparation, a machine learning model, to then be able to look into different sites across the city. So I'm sure that you are familiar with the direct sensing network of New York City, one of them, the NYCCAS one, that collects data for different environmental air quality parameters, bi-weekly data, but for very many years, over 10 years already that they have been collecting this data. And I'm also combining that with remote sensing data sets. Here we are looking at the LST gradients. And for LA, it's a very different data source. It's a citizen science initiative, the Purple Air Initiative, that has over 700 stations across the city. Also, the temporal resolution is finer, 10 minutes. But of course, it's citizen science data, so it requires the data process. It's a little bit more involved, the data processing and validation. So the first step is always developing the correlation to understand what are the most important indicators that drive the air quality gradients in the city. This was the question I was trying to answer in this particular plots. So, for example, on the right-hand side plot, we are looking at the dependent variable here, it's PM 2.5, and we can see that there is a high correlation between building volume and PM 2.5. So the bigger the building volume, the higher the contamination concentration, which is what we would intuitively think. Again, the greenery, a high negative correlation with greenery, which is what we would intuitively think, so more parks, better air quality, right? However, for income, if we look at the colors, LA is shown in blue and New York City is shown in green, we see different trends. So for LA, a high negative correlation is observed between income and PM 2.5. That means low income neighborhoods show a much higher PM 2.5 concentration. And for population, we see similar trends. So more population, higher PM 2.5 concentrations. I'm going to skip this one for now. So here what I'm showing is looking at New York City, some of the sites in New York City that have a very high density, because very oftentimes high density means bad air quality. So looking into the sites in the city that have this very high density, but have a better than the mean city air quality concentration. So why do these sites have a high density, but still have a good air quality condition? So I'm showing 4 of these examples on the right-hand side. Already qualitatively looking at them, we can see that the fabric conditions in these sites are a little bit heterogeneous. So there is kind of an urban roughness, meaning a height variability in the urban fabric, and also quite a high ratio of the greenery. So is the case, I'm going to jump quicker for LA because it's the same scenario. In this case, the height variability is less so, but we see the green ratios also increasing in those areas that are higher in density, but that show a good air quality condition for the mean of the city. So here is trying to describe the same. So again, aiming to really reinforce the idea that in the city, interurban environmental gradients are oftentimes stronger than if we compare the mean between 2 cities. So we need to have it very present that depending on where you live in the city, you are going to be exposed to a very different urban health condition. No? So just to quickly go through these 4 plots, for example, the one on the bottom right is the one that follows the criteria I just described. High density population, but good environmental condition. The 2 stations located to the left, the first in Bronx and the one below in Brooklyn, are from the low density range, however, are amongst the 10 worst locations in the city in terms of air quality. And taking the one at the Bronx, for example, we can see that it has below mean NDVI, so it's not very green. It's highly impervious, and it's a low income, high asthma incidence neighborhood. The 2 axes to the right-hand side, on the other hand, are located in high-density neighborhoods. However, the top Chinatown one follows the typical pattern, so high-density, poor air quality, and microclimate, as it's generally the case for high-population locations. And the one located nearby in Rockefeller University, the one on the bottom, however, shows very, very high-density population, but high NDVI and much better than mean air quality and air temperature scalar concentrations. Similar study for LA, again, I'm going to skip it just for in the interest of time. The second project is about zooming in a little bit in the neighborhood. So looking at the city, of course, we have to model a lot because the sensors are scattered. If we look at the neighborhood, then we need to think about methodologies to be able to see these gradients within the neighborhood. So this project was about developing a sensing kit to collect those environmental gradients, a sensing kit that could be deployed to mobile platforms, so vehicles such as buses, cars, and so on, and that contains sensors for different environmental parameters. And I've done 3 iterations of this sensing kit, and every one of them had different sensing groups. And then, of course, the data analysis and visualization part that it's always followed. So this is the 3rd iteration of the sensing kit. I'm not going to go into details. Of course, there is a calibration aspect that is very critical to these local sensors that require quite a bit of calibration to validate the data. And the first iteration of the sensing kit, which was deployed in over the buses in the city of Seoul, collecting data for about a month. And this data was reported in real time to citizens, again aiming to show these neighborhood scale environmental gradients that are present in the city. Second iteration in New York City, this was a more controlled experiment of 1 week, also including an IR camera. And the third one, 1 year and a half ago in Princeton campus, using the logistic vans of Princeton University. And here we can see, if you are familiar with Princeton, the gradient that is quite obvious going from campus to Route 1, where we see consistently we're seeing the spikes in the concentration levels. And in real time to the lab network, we were making this data available as gradient maps. And this is the third project I wanted to show, again, zooming in this case, to the public space, to the study of the public spaces in the city of Brussels. And of course, the more I engage with this kind of site surveying, site analysis approaches, the more we realize, myself and everybody involved in this kind of work, is that the more information is being missed. No? What I mean is that, of course, there are many objective parameters that we can quantify through site surveying, but there are also many subjective parameters that we have to learn how we can introduce in this kind of analytical processes. No? So this project aims to engage with that ambition a little bit. It started with the overarching question, how can urban green infrastructure be designed to improve citizen comfort and reduce stress? Here I'm talking about psychological stress. And we very soon we realized that there were many other questions that were behind this question. The first one was, okay, we talk about urban green infrastructure, but in architecture we often measure green infrastructure through GIS or geospatial analysis, counting trees, counting the area, but we don't quantify the perception of greenery. So the first challenge we faced, okay, how do we develop a pedestrian level green perception quantification approach? The second one was, how can we really start to introduce or develop a protocol where we account for objective, subjective, physiological, psychological dimensions in the process? And how do we package all of this in the analytical protocol? So like every project I'm showing, it's not only me working on the project, there is a team, and especially in this one, I wanted to evolve a little bit on that because it's very important that these are interdisciplinary projects, especially this one. So this was a grant I got like 1 year ago that started with myself and a little group in the architecture school here in UC Louvain. But soon we engaged with the collaboration with Professor Edwards from the psychology department, followed with an immersive media group involvement and the media technology group involvement in the university, as well as external collaborators from the UC San Diego, Florida International University, and we had also 2 conversations with the 2 members from the Academy of Neuroscience of Architecture. And the research methodology involves kind of 3 main steps. The first one is the gathering of urban data, geospatial analysis, remote sensing, image processing, point cloud scanning, then participant data collection through eye tracking, heart rate variability, so biometric sensors and environmental sensors, and then questionnaires and feedback mechanisms for this kind of more subjective dimensions. And then the evaluation part, that is the data analysis of the variability of the heart rates and so on. The study areas, I don't know whether you are familiar with Brussels. We started with the Brussels capital region and with 2 communes. Saint-Gilles is where the UC Louvain Brussels faculty is located, and Molenbeek. These are 2 communes that are not very green. They are very dense, very high noise levels, but socioeconomically and socioculturally very different. So that's why we decided to start working in these 2. And then now we are expanding a little bit more in the city. So these are some of the sites we chose in Saint-Gilles, some of the squares we chose in Molenbeek. So always focusing on public spaces. And this is just to show you an example of one public space in Saint-Gilles, developing a kind of traditional urban analysis about, facade heights, a number of trees, type of street furniture, green areas, and then image 360 images and videos we collected And then the metrics we started doing for the capturing or the quantification of the greenery, starting from GIS and remote sensing data for NDVI computation for every one of the sites, to semantic classification to understand the trees, the grass areas, and to point cloud segmentation. And from here, we started to, these are some of the sites, some of the public squares we analyzed, to organize the squares based on their greenness or on the quality of their greenness. Here I'm just showing the percentages that you can see it goes from very impervious to very pervious. And then a participant testing protocol that we are doing at the moment that involves a VR immersion where the participants are exposed or are immersed in these urban scenarios that they look from one to another. They are exposed to the environmental condition there's in terms of the sound, the lighting conditions, and the visuals. And we are collecting biometric data and capturing the eye gaze, as I mentioned, to then relate that with metrics related to psychological stress. These are some qualitative, quantitative data we are collecting. This is the search that is ongoing. So started 2 months ago, and we are aiming to finish in 2 months. We have to get to up to 120 participants. And this is the data that one of the participants generated. Of course, this is the sphere that I'm unfolding here to a flat image. And you can see the eye tracking data that is moving here. The same thing for one of the images over the semantic cemented image. And then we develop quantifications of the areas of interest, the fixation saccades, and so on over them for every one of the images. But of course, I cannot still show you the kind of collective results because we haven't yet finished the experimental campaign. So that's where I wanted to finish. So this is like work in progress. So it's going to be like a sudden finish. But next steps that we are doing here is deploying or developing an on-site immersion approach with this kind of ambition to collect physiological and psychological data and kind of combining this objective and subjective approach, but on-site also to account for thermal information. And then we are also developing for the whole city, looking at the different squares, a methodology for this kind of pedestrian level greenery perception quantification approach using not our instruments, but Google Street View imagery. So that's all for my end. I'm sorry for the, I think, 2 minutes extra.
Yeah. Many thanks. Many thanks, Maida, for your presentation. It was certainly interesting. It's my pleasure to now introduce Evangelos Pantasis. He will talk about design behaviors or designing behaviors, the wide application of digital design. The advances of digital fabrication and robotic processes have facilitated the materialization of bespoke geometries. In turn, it has raised the issue of how architects can reduce design complexity using computational techniques. This lecture will address how computational design methods can help manage complexity across different design scales and domains. The presentation will focus on the development of a design framework based upon a multi-agent system approach. A series of simulated design experiments will be presented where the framework has been applied, which aim to simultaneously satisfy complexly coupled and often contradicting objects. The motivation of the work includes exploring bottom-up generative methods coupled with optimizing performance criteria, including geometric complexity and objective functions of environmental, structural, and fabrication parameters. Evangelos is a multifaceted designer working at the intersection of architecture, engineering, and computational design. He holds a PhD in civil and environmental engineering from Viterbi School of Engineering at the University of Southern California, where he has also worked as a teaching and research assistant. His research work focuses on the use of multi-agent design systems for the integration of generative design techniques and form-finding methods with numerical analysis and digital fabrication methods. He has earned his Master of Advanced Studies in the field of computer-aided architectural design from the ETH in Zurich 2012, and also got his diploma in architecture from the Aristotle University of Thessaloniki, Greece in 2010, where he is a registered architect. Professionally, Evangelos has gained experience in several international offices, including Craft Architects in Berlin, Studio Peso, Beijing, and Bureau Harput Engineering in Los Angeles. He has co-founded Topotech Design Office, a studio that engages computational design with various tangent disciplines, including architecture, furniture, and product design. Currently, he leads the computational design team at IBI Group. His research has been presented in multiple design computing conferences, and his professional work has been exhibited at venues such as the Venice Biennale in Architecture, the Modern Art Museum of Lausanne, and the Benaki Museum in Athens. Since 2014, he lives and works in Los Angeles. Thank you, Evangelos. The stage is yours.
Thank you for this great introduction. Thank you, Sandra. Can you see my screen? Yes. Okay. So here we go. So as Sandra mentioned, I want to start, or I like starting my presentation with that because my life has, or my career was always between academia and practice. And by doing that, I had always kind of had my feet on two worlds, the one which is more applied, the other which is kind of more academic or thought-provoking. But then there is always, like, at the intersection, like, it was always the architecture that interests me. So for example, one of the main things that was always interesting to me was like the complexity and how do we manage complexity as architects and designers. Here we see the Louvre of Abu Dhabi, which was completed some years ago, and as like the main engineer mentioned, it wouldn't be buildable if there was no way to find simplicity among the complexity. Now, something interesting along my career that has happened is, although access to computation and tools has become easier, like understanding the principles behind them hasn't become any faster or easier. So why is it important to consider, for example, certain other parameters in the design state, such as environmental parameters? Here we can see it kind of explicitly. By the time, for example, a building is completed, 90% of its life cycle, economic and ecological costs have been made inevitable. And let's say 0.1 is kind of the design cost. So this is how much we are part of the cost, let's say, of a building structure which lives over the years. So the notion of time is very important and should be considered, but also is the geometry. So of course, tools has given us opportunities to model complex geometries, but that, for example, hasn't allowed things like what we see below to happen, with the failure of a structure in the Paris Charles de Gaulle airport just 9 months after its completion. Whereas above, we see one of the projects that was designed and built to stay temporarily, like 50 years ago, and it's still standing. And that's like the Olympia Stadium from Fray Otto. Of course, the design approach of these two buildings vary. What is important for me, or the context of this, is how can we as designers improve our design approaches, and how can we have more impact on the design. And here we see what is known as the McLeamy curve, superimposed with another set of curves. Mainly these curves define productivity in the AC, and you see the basic difference between the traditional and integrated design processes. But also we see, as we move over time, how the level of influence of the design decreases while the cost of the design changes increase. What that means is we have a much better position and value if we can impact things in the early design stage. And that brings us, okay, so how do we do that? How architects manage this design complexity in the age of information? And for me, a very important thing is the hiatus that we see here on the red line, which is how we move from associative geometry and customization to, let's say, complexity and computation, or how do we move from descriptive geometries to abstract geometries and notions. And saying that, I always like to share this image, which is kind of speaking of or illustrating the difference between having a reductionist approach versus a complex approach. So on the left side, you see a duck and how this can be in a reductive way analyzed and maybe create an automata. That's the digesting duck from John Vaucanson. Whereas on the right side, we see how with analyzing a set of local rules, we can end up simulating natural phenomena. So we see, for example, the cellular automata that everybody, I guess, in this room is aware of, and how that can reflect in a pattern of a cell. And more so, continuing on this analogy, our design and our industry, the AC industry, looks more like on the left. We have adopted, since the modernism, or since the advent of the 20th century, a reductionist approach where we like to seal or compartmentalize, excuse me, things into disciplines, and in a top-down manner, we proceed from design to construction. Whereas on the right, we see more so how that happens in nature, and how, for example, termites work with their local environment and then get feedback from that in order to create their own habitats. And now it is always coming the question of scale, but in that case, for example, the termites outnumber us by far. So like a termite can build a structure almost 2,000 times bigger than itself, whereas the biggest structure on Earth, the Burj Khalifa Tower, is like 415, 20 times bigger than an average human. So with that, I would like to focus on how do we make new tools and how do we make new abstractions. And just to refer to Marshall's McLuhan, we shape our tools and the tools shape us thereafter. And here we see sort of the evolution of digital design tools from being disconnected tools that I guess everybody has experienced, proprietary software that does not communicate with each other. It has moved towards more BIM-centric approaches where we have centralized tools. And more recently, we have seen an advent of a lot of toolkits and computational methods and solutions where we are trying, or we are starting to see an ecology of things. Now, a typical design process is like the one that you see on the left is diagram. So we generate ideas, we analyze the merits and the constraints or the drawbacks, we evaluate and select, and then we iterate. And on the right, you see how that plays in a computational scenario. So we see a project I have worked in, a solution we have developed recently with IBI Group for the design of a building, where they want to see how the structure that they are building, it's at the University of Ottawa, it's a lab facility, and they want to see how it will be affected by future development. So we generate thousands of options by trying to consider environmental parameters, programmatic parameters, site approach, and then we are trying to evaluate them and select them. And that is what you see, for example, here, where we are have every design with the specific design outputs or performance criteria that we want, and then the designers in collaboration with us can go ahead and select. which one we think is the most fitting. But how do we do that, and how do we generate thousands? How do we drive this process? And this we can see it's outlined on a high level here. When we're talking about computational design, we're talking about a formalized process, but formalized process doesn't mean a properly not flexible process. In any case, we have a design team where we define a certain set of parameters, we generate alternatives or options, and that forms the solution space. And then with a certain set of performance criteria or measures, we try to do that over and over. And in order to control that, a very typical approach in order to drive this generation is making a heuristic function and trying to optimize a certain value. But this is not always in architecture the case. And this is why in architecture, a lot of times we're not investing in the most optimal solution. And also architecture a lot of times is used differently than what the designer was assuming. So in my research, I try to look into how we can use agents as an abstraction for design. And what do we mean by that? Let's take by decomposing the design process into different fields, we can create like agents, different types of agents, generative agents, specialist agents, simulation agents, etc. But before moving more into that, I would like to go over what we define as an agent in this context and what we define as a multi-agent system. So an agent can be an autonomous, intelligent software or physical system that operates within an environment, has sensors, states, behaviors, and actions. So based on the sensors and the states it has a certain behavior and action. And a multi-agent system is a collection of those agents. And how about we can start thinking, instead of drawing with the design software that we are kind of used to with volumes, prism, etc. How about we define abstract agents that does that? And instead of having a library of tools, we have a library of behaviors, which could be flocking, transport, clustering, or also custom ones like attract to some point or avoid a certain point or go towards the sun, or maybe a structural property such as reciprocity. And in order to do that, we need to have methods for doing that. Methods for forming behaviors, meaning methods for forming heuristic functions that can drive these behaviors. And also we need to have a certain abstraction from signals and cues that we get from the sensors. Now what that does, and it's shown here, that gives us different way to traverse the solution space. So we use behaviors as different ways to either perform a greedy operation and go through the solution space faster, going towards the optimal, or trying to grab as much suboptimal solutions as possible. And how does that work within the design cycles that we have, the common ones? This happens iteratively, and what you see here, we start from disorder and we have a high level of complexity, and as we move towards the end of the project, our freedom kind of decreases, and the let's say the disorder, the complexity of the problem, maybe at some point during the middle of the project is at the highest level, and it comes to an order as we finish. But then we take these design phases and we create with the agents different domains where we apply. So we have a user domain, a functional domain, a physical domain, a process domain. And all this is to say it could be an environmental domain. It's a way to abstract from our design problem and be able to form heuristic functions to deal with it. So how does that look? Let's say instead of having a more linear approach from architecture, engineering, and construction, we're thinking more in a cyclical way, where in the middle is a computational method. And this is all communicated through the agencies that we're saying. Now, these agents could be a software. Each agent could be a specific software. It doesn't have to be all living within a solution. And this is a way how this could be played. So on the left, you see the outputs. In between, we have a certain behaviors that connect the inputs, to the agents. And then we have, let's say, the brain of the thing. And in order to illustrate how that works, I will show you two experiments that I have done. So the one, I call it behavioral form finding, and the premise is very simple. In a typical form finding approach, we have support points and point loads, and that gives us a form found geometry. The hypothesis here is, what if we add location orientation, and how can we start augmenting the purely form found shapes with suboptimal shapes that they are kind of following an environmental parameter. And that looks, here is a kind of a test case of how that would look. So this is, in a way, you see a generative agent in a custom applet playing, and then by bringing in a data-related environmental data from, for example, LA or whatever the location is, we can start augmenting this shape with adding a photophilic behavior. So if we go back to the library, we can see that we select, for example, 3 different types of abstract agents, 1 behavior, which is the photophilic behavior, and 3 methods, and that kind of gives us the solution that we saw. Now, in order to make sense of that and try to see how good it could be with regards to existing conditions, I tried to apply this method to cell structures, existing cell structures that have been developed or designed and built by the guy that came up with the fabric form finding technique, the analog one, Heinz Zissler. And these are 4 structures in Switzerland, that they are sport facilities mainly, but also, yeah, it's like a swimming pool, and it's like a tennis, and I think it's a multi-purpose hall. So what we do into that, I kind of show the flow chart. So we have the inputs where this location is and how big is the area we need to cover. We have the form finding agent, we generate, we get a node and a line model. This is passed to a structural analysis agent, which we call a specialist agent, and at the same time at a environmental agent, like which evaluates the geometry for environmental purposes. And once we get the analysis, we update the behavior, let's say, based on the analysis. And how do we, here you see the function or the heuristics that enables us to define a behavior. And the idea is that what we name as a photophilic behavior is a way to express a design intention and then measure that design intention. And here you see some of the outcomes, and like visually, but the most importantly is how do we look through those in a more meaningful way. And again, by having a parallel line plot with all the important design features that we're interested in, a designer can go through them and see which behavior or which alternative is best fitting for the design problem that they're trying to solve. In this case, we're trying to increase the amount of daylight that goes underneath the structure while maintaining the maximum displacement that has been observed in the existing structure. Now, on a similar but a quite different path, I would like to see another way of expressing behaviors in design or designing behaviors, and this is through embodied behavior. What do we mean by that is how we can alter the geometry of certain things, and then geometries and robots in this case, in order to affect their behavior. So similarly to the previous, we get a physical agent, in this case the simplest robotic system. Again, we grab different types of behaviors, a method for forming, and also the abstraction from the signals, which is just now a spatial one. And this is the, let's say, workflow diagram or the design steps. So we started by designing the robot. We simulate, we parameterize specific geometric parameters. We simulate to see how the robotic system reacts, and then we document actually the robots and see how that differs from the simulation. And with that, we update the geometric parameters of the robot. And now talking about the robots, just because robots in architecture, we are always considering industrially robotic arms. This is a very simple or the simplest robotic system, where here you see just the components. We have a vibration motor, a battery, and just the bristles. And by changing just these 4 parameters, we can have different behaviors, like change the locomotion of the robot. So we are 3D printing the different bodies, and then we see how that works. Of course, not everything works. The length or the angle maybe hinder the robot from even pushing forward. But then by empirically testing, measuring the path and updating the design, we can see, for example, all these different behaviors. And the idea is then to use a simulation and the system to see how that would play in if we would have 100 of those. And so here you see all the different bodies that we tested, and also we see how that impacts the motion. We ended up with this because we wanted essentially the agent to do something, in this case, to push another passive agent, which is a brick, what you see here. And this is more or less a taxonomy. So we build a taxonomy and we see, let's say, for which geometric properties are good for what. Now, in a more, in one step further into analysis, what you see here is like, we cannot, of course, build all the robots or all the designs. So above, we simulate some designs. In red, you see the basic robot, and the white you see the passive element or the brick, and below you see the data analysis we did by analyzing the video using computer vision. And what we're trying to see is if the combination of the robot and the body of the robot and the shape of the geometry can form clusters, and how long do their clusters stay. So what you see on the plots is like the cluster size and the count of the clusters, and how long they stay like clustered, basically. And this is another test seeing the same thing, but how the environment affects the robots. So here you see again the same amount of robots with passive bricks operating. And what is interesting, for example, in the circular arena, we start at the very end seeing an emergent behavior where all the robots start moving around in sync for a while, whereas in the triangular arena, all the robots get stuck after a while. So here again, you see for example, the circular, how it works. So we see, for example, the kind of moments of emergent order. And if we take that one step further, we can make these behaviors even more exaggerated by, for example, changing the weight of the brick or adding magnets to the bricks. So then the bricks can cluster and stay, and then the robots can move them. And here you see how that, for example, plays in. I don't want to take longer to go over this. What I want to say is that, of course, again, we analyze, empirically test and analyze, and the culmination of this was to try to design a full system holistically. So we see that certain geometries work and have certain characteristics. So how can we bring an environmental further parameter into the robot? So here you see, for example, how do we start from that, but then how we developed a custom robotic system that we can control with a machine from our phone, but it kind of just reacts to the phone, to light, excuse me. So that's the design we end up, which we 3D printed. This is the electronics and the sensor it has in it. So we added one more motor. We tried to keep it simple. And in a sense, tried the same idea with a system now that reacts. So that was the first test. The robot starts moving when we have enough amount of light. So we have a reaction, the behavior is moved when you see the light, and then turn on the light when you grab a brick. And this is the first dry run of the case. And this is like starting to see how it reciprocates when we have a lot of robots. And in doing that, the exercise and what I want to convey is it's very different when we're trying to design like holistically, and that's what I mean by that. We need to design a system, robotic system that is robust enough. We the physical experiments inform it. I hope I didn't go too long.
Thank you.
Thank you very much, and I'm happy to discuss later.
Thank you, Evangelos, for your precision in addressing collective systems and such an interesting research and work. Now we are going to proceed with Hannah Dahi's presentation, Natural Smartness, a New Era in Sustainability. The lecture summary is the following. The lecture emphasizes in diverse developments done in the framework of the lecture's established department, aiming towards futuristic sustainable architecture. In this context, working with local materials, especially bio-based ones, and with different means of embedding smartness that took place using approaches like ecological fabrication technologies, integration with computational design methods will be highlighted. In addition, multidisciplinary work, automation and technologies and other factors will be revealed to showcase how current and future-oriented techniques could have a direct effect on how smart, sustainable architecture of the future could be developed, created, and serve the environment and the communities. The case studies that will be analyzed through the lecture will cover a large spectrum in that regards, and other related topics will be open to discussion after the presentation. Hannah Dahi, born in Cairo, is a registrar and a freelancer architect in the Architects Chamber in Germany, and as well as registered engineer in Egypt, with 18 years of experience academically and in practice. She earned her Bachelor of Architecture Engineer at IMS University of Cairo with excellence and honors, Master's in 2006, PhD with excellence in 2014 from University of Stuttgart. She established her biomath department during her professorship in the University of Stuttgart since 2016 and founded her architectural office in Cairo in 2003. She holds currently a number of European and international patents in the fields of sustainable building materials, won several international architecture and design awards, including Tamayus for Women of Outstanding Achievement in Architecture and Construction in 2020, Material Praise Award in the years 2016, 19, and 21 from BW Design Center in Germany, earned the Focus International Design Prize Award Silver category in 2021, Green Concept pre-selection for 2022, Eco Prize Multi-Nominators, Excellent Teaching Award for German Universities in 2016, Metarilaka Design and Technology Award 2015, and many others. She leads several architectural industrial projects and is founding member of Archi IDA, Research Center for Architecture in Stuttgart, as well as a principal investigator of the Cluster of Excellence in Stuttgart International CDC, Integrative Computational Design and Construction for Architecture. Dahi constructed numerous architectural projects in Europe and the Middle East, and is a visiting professor in multiple universities in Europe and a member of diverse international scientific bodies. Her architectural practice research areas include digital fabrication, naturally inspired architecture, ecological building systems, biocomposites, biometics, sustainability, smart materials, soft materials, product design, circular economy, and circular design. Thank you, Hannah, for joining us, and the stage is yours.
Thanks a lot, Pablo. Thanks a lot for invitation. I hope you see the screen full and you can hear me properly.
Yes.
Okay. So many thanks again for the invitation. Let me start directly about what is here meant the natural smartness and what is meant by the new era in sustainability. So to get started, it already with this very nice introduction, I would just go quickly that the Biomat, which is the department that I established at the Institute of Building Structures, it started in 2016, and it was a kind of merging between architecture engineering. We're making project management and applying the work that we do in research into realistic projects. I have 6 PhD candidates at the moment and a number of assistants as well as master candidates. And you can see that we are here once taken a nice photo of the group in between a couple of our products and constructions. You see here in the background different kinds of architectural topologies of different applications, as you see in the background. And all the PhDs, each one is responsible of at least one research project, which is a kind of work between industry and research. The major work is in diverse themes, but basically we are dealing with biomaterials, its design and fabrications, but also the integration of smart materials and bio-inspiration through biomimetics. The idea of applying all those systems is through the application mainly of materials as a design tool and the integration of different methodologies, in that sense, also computational design and others, to reach sustainable architecture. The idea of integration of biology and technology is that sense is based on integration of, as said, the bio-based materials and closed loop materials in integration with the bio-inspired form and structure, and all this in cooperation or in like really diffusing with the computational design and digital fabrication methods. And from that, here comes the merging between biology and technology to try to reach to that sense of integration. Starting from this year, I got a full professorship in the Aalborg University in Copenhagen. So the Biomat at Copenhagen is starting from this year. And a very nice, in the intro, it was already revealed the number of prizes so far in that area. So I'll skip this and then go further in the applications that was so far applied in the biomaterials in architecture. Here you see a wide range of funded projects in that area, and you will remark through the naming how the biomaterials is set as one of a bottom-up approach, where we start by the materials and then we go through a large process of integration of multidisciplinary work in order to reach to different building components up till a full building construction. And one of the largest projects that I'm involved in is a project that is beyond the local concept, rather on the EU region, which is called Smart Circular Bridge, that aims to build 3 bridges out of biocomposites with integrated sensors to monitor its behavior, its structural behavior, or so-called structural health monitoring. And we are supposed to build 3 bridges. One is going to be opened by the end of this month in March, and 2 others, and this is in a city called Almere in Netherlands, and 2 other bridges, one of them in the city of Ulm in Germany, and a 3rd one again in Netherlands in another city. And so on goes the funded projects in that sense that we are having the integration of the three main components, which are the materials, which are basically materials coming out of anywhere renewable resources, and fabrication techniques, and of course, computational design. And as good as possible, there is a marriage between what's going on in research and on the industrial applications, and of course, what's happening on in the teaching, so that the future architects could also have a good clue of this way of applying new kinds of alternative and non-conventional materials into the architectural world, given the fact that the building industry is responsible of the highest destruction of what's going on in the environment. And it's still very much underestimated if we look at it from another overall global perspective. It's still not given the very high attention in comparison to the real destruction that goes on in that field, due to the excess use of the cementitious materials and metals and so on. And here there is a trial from our side to try to go in deep into that scope and allow architects to understand how a material behaves. And from that sense, in a bottom-up approach, to understand how it can get shaped through different digital fabrication technologies, and then going up the scale till a final construction system. But it all started many years ago when I worked in that field, trying to know why is it to see that a very kind of terrible image coming from 4 different continents around the world, which is the burning out of fibers in open fields. And the fibers here are specifically coming from the agricultural resources, specifically straw fibers. The straw fibers are generally kind of fibers that come up in the as a rest-over material left in open fields that comes from or after the plantation of different kinds of cereals. And as the grains themselves are held by specific kinds of plants, they are left over in the fields, and the farmers, they simply burn it over in order to clear up the land quickly and use the land again for another cultivation. And because of this action, a destruction further comes to the atmosphere in the form of carbon dioxide emissions. While if we look on the other side of the world, or the other side of the thing, which is a building industry in our case, is in need, a big need of different kinds of resources that has somehow similarity with timber. And if one looks really at the chemical composition of those kinds of fibers, it is quite similar. So on that basis, I worked a lot and tried to figure out why is this action done, because we are in need of timber, and we could use this as a basis to start to look into materials that resemble like timber. And from that, it came one of the developments I did so far in that field of combining straw fibers into a form of a fiber board that simply looks like this. If you can see it, it's a fiber board that has compacted straw fibers inside it, and it can be bent into different directions as seen here. And this development was patented, and it was like the click that opened up a series of developments in that field, so that it could have different kinds of, it looks like at the end as if it's timber, why it's not. It's like compacted recycled straw fibers in that way, in order to reach high density fiber board that could be applied later, as will be seen in different applications. So the whole thing started going on in understanding in the field of natural fiber reinforced composites or biocomposites, how we can combine natural fibers in different ways and forms, shapes, and colors. And all this know-how was further given to my students, and it was in an exchange with industrial partners. Still a very big thing started going on in order to apply different materials in interiors, exteriors, and then it turned out into research projects that went in a very nice outreach, trying to solve through those kinds of environmentally friendly materials different applications in architecture and beyond. And as you see here, this is one of the upscaled productions that happened during one of the projects to upscale the bioflexi development. And it went on further into an upper level, even to attract further communities and researchers. So this is another community from the chemical field who invited me to join them in one of their work to extract even chitin from the shells of marine creatures, and to get this as a source so that I could figure out as an architect how this bio-based material could help us in our building industry. And the work went on using different technologies, and this is one of the latest funded projects that has to do with 3D printing of different kinds of fiber-reinforced composites, bio-based ones. And you have, you can see a team and a big team, and the machine behind us is one of the biggest 3D printing machines worldwide that is owned by one of the companies inside this project. And we have like different communities trying to have a very nice connection on how the applications of biocomposites could vary on different levels and scales. And one of them is the excellence cluster of the University of Stuttgart, which is also by history the largest funded project for research in architecture in the history of Germany. Furthermore, this is the project that I was just talking about, the bridge one, that is in cooperation with 4 different European countries between Germany, Netherlands, Belgium, and France, and will hold this 3 bridges to be built in the framework of this project. But then let me take you to a closer look on work that we have done through that branch of specifying certain kind of fiber and certain kind of fabrication technique, and then through form finding methodology, we reach up to the optimum form and structural behavior that we could get out of that material, and we validate the whole thing through a mock-up building that could expand up to 10 meters span and a height of 4.5 meters. And throughout that process, there are so many disciplines that get integrated into such cooperation, like colleagues from structural design, colleagues for quality assurance from the Geodesic Institute in the University of Stuttgart, colleagues like the aircraft design who would help, or who helped actually in initiating with us like a scope in the area of additive manufacturing technologies using a system called tailored fiber placement, and so on, investigating different kinds of techniques in that sense. And one of the projects is called Flexible Forms. That was the Biomed Pavilion done in 2018, and this is how it looked like. It was a triangular format that was double curved and is formed of more than 360 pieces that were interconnected in that way on a double surface, as if it's a sandwich panel, to create a structural depth of around 18 centimeters. And it was a shell construction that was having the main construction system based on 3 superficial foundations, because we were not allowed to dig screws inside this platform, because underneath us there was an auditorium, and we had different limitations where we had, of course, to cover that through the design procedure and, of course, within the construction. But it all started with the material, as said, and we tried to figure out what is our maximum scope that we could reach through the material that was predefined. And through an integration of different aspects in our workflow between, of course, the project management was a part of it, just like in ordinary office, fabrication and material testing, structural performance, till we reach up to the global design and detailing, all played a big role in an iterative process. And structural analysis in cooperation with colleagues from Netherlands, as well as a scanning that took place in all the phases of the construction, before construction, and in the real terrain that was on site. It was always a way to figure out if we are working in the needed accuracy or not during the whole construction. And of course, because we knew that we had different parameters that we need to follow, one of the issues that we had to consider is that we have the possibility to have a complete reuse of every single unit of that construction in another application, and one of the investigated applications was a facade panel out of that. And here you see the outcome, how the precision looked like in order to reach to that size of application, and here in relation to the background, as you see. And we were luckily, we won a prize in 2019 based on that project. But to show you what actually it was or how the process looked like, here is a video for that. Oops. I don't know what happened, but because of time, I would skip the video and then go to the following project, which is the tailored biocomposite canopy. And that is another story. Here we shifted to a new kind of fibers, which was much longer fibers. And in this case, we have, we made a cooperation with different partners, but including colleagues from the aircraft design, from whom we knew about this technique, which is basically that we have a stitching machine, we have a stretched membrane, and then we stitch our fibers in the needed direction on this kind of stretched membrane in layering. And depending on the clearance between the head of the machine and the membrane that is being stretched, we have like a limitation of how many layering of fibers we want to stitch. Here we had flex fibers, and the background textile can be of different kinds of textiles. And we, of course, went into different design processes between the basic shell optimization and topology optimization of the single curved canopy. Here we applied like a single freestanding canopy that would be a shelter for a station or a different kind of application. And we had this optimization process happening in order, after many iterations, to figure out in which direction could the single fiber lines would be moving on, depending on the scenario of that optimization. And you can imagine that we have something that is a free form, but we need to produce it first in a flat format, and we have to create multi-layers. And in order to have a level of rigidity, we created the layering in 2 layers above one another, and each single layer is actually based on 4 different levels of fibers that are stitched. And we had a whole fabrication time of 2 days and a curing of around 3 days to 4 days, which is again something that is way quicker than the previous project that you have seen. And it was, in this case, a full scenario that was done how to apply longer or endless natural fibers that are made of hemp or flax. In that way, after exactly knowing what would be the fiber lines, depending on the forces flow in that construction. Here, the whole construction weighed only 35 kilograms, and we used only 5 yarns in order to accomplish that structure. The final project has to do with something else called pultrusion. So you see that in each case, we are evaluating a certain type of production and how far we can reach through our building element for a complete structure system out of this annual renewable resource. So in this case, you can imagine that is actually the kind of fibers that we have applied. You can see it in the screen. Very simple types of fibers that are being compounded in one, and that's one of the very basic or starting in the laboratory scale production. And you see how thin it was at the beginning, and then after the upscaling procedure that you see it in the last photo, this is how the size of the profile that we had. And this system is called pultrusion, which means that the fibers are pultruded in a certain known direction, as you see it in that case. So we know exactly how to orient it in a way to let the forces flow in it in this longitudinal direction. And you can imagine how far we went into applying those kinds of profiles in longer lengths, bend it and fix it. And this is called bending active structure systems. And we applied here cross beam systems in order to reach to this double curved shell construction. It had a span of that was one of the results that our project partners tried out during the COVID time. They have made the first production and tested for us, after, bending it physically and videotaped it for us to know or prognose the behavior. And that was one of the initial results. And you see in the construction side, we dealt with it as if it's artificial bamboos. And here 2 of my PhDs are on the crane during the construction process. And you can see it here in the background, the 2 known buildings in the middle of the city of Stuttgart. And we tried as good as possible to use the least possible cranes and the least possible posting points, and relied on the correct positioning of each one of the start and end points of this bent profiles. The whole construction took around 2 weeks, and the planning process and the invention of the materials and everything took very intensive year or year and a half. But the concept, it started already before that. It took like around 2 years to build up the consortium, to get the idea, to have the full vision of how from one single unit, one single fiber, we can reach a full construction system like this. So we can see the full filigrane structure, how it looks very light. It is very light, but it is full of detailing and know-how in it. In that sense, and it was a very nice group. Here, I don't know why I'm moving very fast, but here is part of the group. We got also a prize for it, and even a pre-selection. We had the chance to be pre-selected in one of the further prizes. And here is the last video that I would like to show you. project over 1 year period from different disciplines. And by this, I come to the end of the presentation. Thanks a lot for listening.
Well, thank you so much, Hannah, for your presentation. And now I'm excited to introduce Neil Leach, who will talk about architecture's Sputnik moment. He will discuss how AI has become a hot topic in architectural circles worldwide. For sure, AI is becoming increasingly capable, but is there a dark side to AI? This lecture addresses the dark side of AI, but not in the traditional way, where AI is seen to be complicit in surveillance, capitalism, and other concerns. Rather, it points toward the remarkable achievements of AI and the way that AI has begun to operate beyond the range of human abilities. The lecture argues that humans must begin to recognize that AI is capable of operating at a level of intelligence and creativity that we cannot even perceive, just as dogs are able to detect smells and sounds beyond the range of human perception. AI, the paper argues, has already begun to leave humans behind. The paper concludes that we need to go through a second Copernican revolution and recognize that human beings are not the center of the universe, and that if the entire human race dies off because of COVID or for some other reason, the universe will continue without us. Neil Leach is a professor at Florida International University, Tongji University, and EGS. He has also taught at other leading institutions, including the IAC, DIA, Columbia, GSAPP, Cornell, Harvard, GSD, and SCIARC. He's also the co-founder of Digital Futures, an academician in the Academy of Europe, and the recipient of 2 NASA fellowships for research into 3D printing technologies for the Moon and Mars. He has published over 40 books on architectural theory and digital design, including Rethinking Architecture, The Anesthetics of Architecture, Designing for a Digital World, Digital Tectonics, Camouflage, Digital Cities, Machinic Processes, Space Architecture, Robotic Futures, Swarm Intelligence, Computational Design, Digital Fabrication, 3D Printed Body Architecture, Architecture in the Age of Artificial Intelligence, and recently he edited DAA of Machine Hallucinations, Architecture and AI.
Thanks,
so thank you very much for presenting your work. I'm very looking forward for your presentation. Thank you.
Thank you, Sandra. I hope I can live up to that introduction. I've changed the title slightly. It's dawned on me in the last week or so that we are now facing a crucial moment in the history of AI and architecture, a moment that I want to refer to as architecture's Sputnik moment, and hopefully that will become clear as I go through my presentation today. There are 3 areas, I think, where we already are noticing something new is happening. Firstly, the world of publications. This is a book that I published in December 2021. It actually is listed as 22, and it came out in the States in 2022. And alongside that, there's this book, the issue of AD, that I'm guest editing with Matthias Del Campo, that will come out in June of this year. And in fact, there is a deluge of books that are going to appear this year on AI and architecture. These are just some of them, and they will all be coming out in the first half of this year. It's clear that something is happening in terms of publications. Alongside that, and this is a further publication I'll be working on as part of the follow-up to my first book. The actual title is called The Death of the Architect, the Demise of the Architectural Profession in the Age of AI. And I think I'll want to try and illustrate the threat in some senses about that AI presents, because it is so capable. It's not because it's inherently evil or anything, it's just very, very capable. And alongside that, there are a number of other things happening. Philip Yuan and I are launching a journal called Architectural Intelligence that will be the first issue, which comes out in June of this year. And we've also been hosting a series of sessions on the new emerging theory of intelligence that's coming out to the interface between AI, neuroscience, and architecture. On Sundays, and if you're interested, there is at the bottom here, you can see the link to all the recordings something new and something very special is happening in terms of theoretical circles. Having said all that, the third area in which I think there have been developments is many ways, I think, the most important, and that is to say the world of design itself. And I'm showing you a project that many of you will know already, Deep Himmelblau, that won a series of major awards in 2021, including the Digital Futures Award and the Acadia Award. I want to suggest today there is a new kid on the block, and there's something even more astonishing that is about to happen. So what do I mean by the Sputnik moment? Let me go back to 1997, and there was a series of very high-profile public events that brought the capabilities of AI to the public attention. In 1997, an event that had been predicted by Ray Kurzweil, an event that had been predicted that would happen before the year 2000, the world chess champion would be beaten by AI, indeed happened. Garry Kasparov was comprehensively beaten by IBM's Deep Blue. What I find significant, perhaps, is the comment that he made after the match: "Everything we know how to do, machines will do better." This was the first of a series of events, the second one being IBM Watson taking on the best human competitors at Jeopardy, and as we can see, thrashing them. Ken Jennings made a comment on the final part of the match. "I, for one, welcome our new computer overlords," a reference to a comment in The Simpsons. But the key issue that I want to talk about today was this particular event, a game of Go, a game that probably, a match of Go, that probably means very little to those of us in the West, because Go is not a match that we play very often. It's not a game that we play very often, but one that had huge consequences in Asia, where, particularly in China and Korea, where Go is the national game. And this was a match that took place between AlphaGo, a system developed by DeepMind in London, and Lee Sedol, one of the world's greatest ever Go players. And it took place in Seoul, Korea in 2016, and everybody was expecting Lee Sedol to beat AlphaGo, not least because the game of Go, although simple in terms of the moves, is infinitely complicated in terms of the potential moves. There are more potential moves in Go than there are atoms in the universe. And in order to address this, they had to move beyond the expert systems that were used for DeepMind to develop learning systems that were able to address this. What was so interesting about this particular match was not the fact that Lee Sedol lost, and he lost 4-1, but it was the way in which Lee Sedol lost. Because there were certain moments in the game where AI was able to operate at a level totally beyond human comprehension. And famously, this particular move in game 2, move 37, has gone down in history as being the most significant moment in the history of AI. It wasn't the only moment. There are a series of other moments in this match, a series of what they call slack moves, where DeepMind was playing, AlphaGo was playing moves that nobody could at first understand, and indeed thought were mistakes initially, glitches in the program, but actually proved to be strategically brilliant. This is move 37. Where AlphaGo puts this black stone here, very unusual because it's on the 5th line, and normally in the beginning of a game you have the 3rd or the 4th line, but it put the stone here, and 100 moves later, these two black stones managed to kind of forge a link between this and win the match. Most human players operate through intuition and operate just simply one move ahead. Potentially, AlphaGo was operating 100 moves ahead in this particular match. And this led to complete shock. As Lee Sedol comments, "Yesterday I was surprised, but today I am speechless," following that particular move in game 2. And he came at the end of the match itself. He came to the conclusion: AlphaGo showed us that moves humans may have thought are creative were actually conventional. Human beings, in other words, were being left behind by AlphaGo, by AI. In 2019, 3 years after the match, Lee Sedol retired from the game of Go, commenting, "This is an entity that cannot be defeated." Does that perhaps offer some presage to what's going to happen to the world of architecture? So the Sputnik moment. Here, of course, I'm referring to the original Sputnik moment in 1957, when the Russians launched the Sputnik satellite into space, shocking the Americans, and it was a kind of wake-up call. This is what led to the foundation of NASA and ultimately led to Apollo 11, to the Americans putting human beings on the moon. But it was this particular Sputnik moment that changed, as it were, the whole sort of the space race. Kai-Fu Lee, in his book AI Superpowers, China, Silicon Valley, and the New World Order, uses the term Sputnik moment to talk about the shock that this particular match, AlphaGo, had on, particularly on China and the rest of Asia. Just over a year and a half after the match, President Xi, as a result of this match, announced his plan to invest in AI with the idea of somehow China overtaking America. And I would say that probably they're well on their way to doing that at the moment. And it wasn't simply China that was kind of had this wake-up call. I think the AlphaGo shock rippled throughout the world, and especially in Korea, where the match itself took place, where they also, as a result of the impact of the match, began to invest heavily in AI. And in many ways, the rest is history, because the race is on to try and to compete to be the world superpower in terms of AI. What I think was the important message here is that human perception that somehow machines could not do anything that was beyond human ability, the kind of comment that's made by Jack Ma, I never in my life say human beings will be controlled by machines. It's impossible. Human beings can never create another thing that is smarter than human beings. That it's obviously wrong, as Elon Musk points out. People underestimate the capability of AI. They sort of think that it's like a smart human, but it's going to be much smarter than the smartest human you will ever know. The biggest mistake I see people making is to assume that they're smart. And what I want to kind of comment in some ways is that what we are beginning to understand, that there is a spectrum in terms of let's say, intelligence. Just as a dog has a greater capacity to smell or hear than human beings, I would claim that AI has a certain strategic ability to go way beyond what human beings can conceive. This idea that we don't know how dumb we are, the dumb don't know how dumb they are, is of course known as the Dunning-Kruger effect. I would want to suggest that maybe we need to extend that to say that the intelligent don't know how dumb they are, or indeed that the creative do not know how uncreative they are. We are effectively being shown up by the capabilities of AI. This I refer to as the second Copernican revolution. Just as Copernicus had pointed out that the universe does not revolve around the Earth, so I would argue that the universe today does not revolve around human intellect. There are other forms of intelligence that we have to recognize that go way beyond us. If the human race dies out today, the universe will continue without us. I want to then give you some illustrations about what is actually happening in terms of the use of AI in the ordinary office. This is nothing spectacular in terms of its architecture, but what is interesting are the observations that have been made about the use of SpaceMaker AI. One of the software has been developed for use in the architectural office. SpaceMaker has recently been acquired by Autodesk for 240 million. Clearly, this is what Autodesk think is going to be the way forward. Now, if you look at this architecture, you might not think it's so special, and indeed it is fairly conventional in some senses. But what is interesting are the observations that came up. This is Harvard Hochland, the CEO of SpaceMaker AI, where he was commenting that basically a bit like AlphaGo, where AlphaGo was able to operate at a level that we couldn't comprehend, so often SpaceMaker was able to come up with solutions, suggestions for urban planning proposals that were beyond those which humans had thought about. All the human experts weren't able to conceive of what AI could do. It was able to operate beyond the level of human abilities. And that meant, for example, certain sort of counterintuitive solutions coming up with that really changed the rules of urban planning, just as AlphaGo changed the rules of Go itself. But the most important comment, I think, that came out of this this discussion, and I think also out of my recently published book, is the point that developers are asking, or clients are insisting that architects use AI. And why are they asking for that? They're asking for that because AI is able to guarantee their return on investment. They're able to maximize the profit on their site and the performance of the building itself. Clearly, AI is something that clients are very keen to have. I want to introduce Wan Yu He, one of my Doctor of Design students, or one of our Doctor of Design students at Florida International University, and the CEO of XCool. XCool is a company that was set up in 2016, the same year as AlphaGo, and it was highly influenced by the AlphaGo situation. Wan Yu herself used to work for OMA. XCool here refers to XCoolHaus, XOMA. It also refers to the Urban Dictionary, the term supercool. Wan Yu herself was more influenced actually by the next generation of AlphaGo, which is to say AlphaGo Zero, a far superior system that not only was able to beat AlphaGo, the original model, 100 games to 0, but was able to teach itself to play Go. It was able to teach itself to play Go through reinforcement learning, by playing 3.9 million games of Go over 3 days, effectively 20 games of Go per second, something we simply cannot comprehend. And what XCool have been doing, exploring over the years, is the potential of using this platform largely for developer architecture. This is a project they did a while back based on style GANs. This building does not exist, and it's part of, I guess, a series of interventions that they've been making over the years. More recently, this is something that we published in the AD, Machine Hallucinations, of their more recent sort of work. But most people have not been paying much attention to XCool precisely because these are fairly conventional, straightforward rectilinear buildings, and most of their work they do is for developers. So why do we pay attention to that? Typically, according to Rem Koolhaas, architects have been looking through a microscope at the kind of at a footnote within the history of architecture, and I think we need to pay attention to what's going on. But what really makes us stand up, makes this whole thing stand out, is when we find XCool producing a project that is in many ways a kind of progressive architectural project. And I want to share with you today, as a way of wrapping up my presentation, a project that they recently, a competition entry they put in for a building, an environmentally sustainable building that was produced in China. It was a Chinese competition, but they beat 200 other competitors. If you look at this block on the right-hand side here, you can see how the rectilinear project is itself being broken down. And what emerges out of this process, it's based on thermal comfort, this particular part of the project. What emerges is a form of architecture that actually looks much more like Frank Gehry than it does the kind of standard developer architecture that we've been seeing coming out of XCool. So here we are, this kind of I think it's a form of topological optimization process whereby these forms are emerging. Now, the project I can't show you, but I wish I could show you, is the next step, which is a competition entry on an international competition where XCool is competing against, let's say, just 2 of the top 10 practices in the world. I've seen the project and I'm blown away by it. I'm not allowed to show it. It's not this one I'm showing now. This is the same one I was before. But something is emerging, and we will soon see very shortly on an international scale what is happening and what can come out from this kind of techniques. There is then, I want to suggest, this is the point. This is the point, the Sputnik moment, when the architecture profession wakes up and pays attention to what is happening in AI. It takes, just as it took AlphaGo to play against the world's best Go player to really bring home the potential of AI to people living in China and in Korea, so to the architectural community, it will take AI competing with the best architects in the world and potentially beating them to really bring home the potential of what AI can do. There are many aspects to this particular project that I won't go into now, but there was, for example, the paneling system, which they, tessellation of the paneling system, which they consulted a human expert on how to reduce the number of primitives, as it were. And they, in the end, they had to go to AI. They had initially 1,000 different sort of sizes of these panels, and then the human expert reduced them down to 120 or so, and they used AI to get down to 12. So all these kind of, throughout this particular project, AI has been used as a way of generating the design. It is a project that, as I understand, is completely based on the logic of AI. What I'm showing you there from a personal perspective, nothing near as astonishing as the project I can't show you, and I'm looking forward to the moment when we can see that one, because it seems to me that what we're encountering is the moment when, precisely the moment when people pay attention to what the potential of AI can be. One comment that Anu made when she showed me the other project, which I can't show you, was that she was terrified of showing it to people. She was terrified of showing it to people because she felt that people would begin to perceive that AI could effectively take all our jobs away. And that, in a sense, is the whole project behind my second book, The Death of the Architect. And that's pointing out that really we are at threat of AI because it's able to operate at a level way beyond human abilities. So what I'm suggesting then is, if you look through the kind of the history of AI and the history over the years, going back even to the Sputnik moment in '57, there are certain crucial moments when we've certainly become aware of these capabilities. 1997, DeepMind beating Garry Kasparov. 2011, winning at Jeopardy. 2016, with AlphaGo beating Lee Sedol. 2021 with extraordinary work of Deep Himmelblau by Daniel Bolojan and the Corp Himmelblau team. And I want to suggest that by 2022, we are suddenly going to realize that the real abilities of what AI can do, because the architectural community will wake up to them. It's not that this work hasn't been going on for some time, but it takes a high profile moment, as it were, a kind of Sputnik moment to really bring this home to the architectural community. So this is the presentation I want to make today. I think that we are about to see something quite astonishing happening in the world of architecture, something that is going to be a game changer, that is going to be, in a sense, learning from AlphaGo. 50 years ago today, a very famous book was published in 1972, Learning from Las Vegas. This book, I mean, I don't know why people read this book, but it's a very popular book. 2022 is 50 years after the publication of this book. There'll be a second book hopefully coming out called Learning from AlphaGo. My view is that AI is going to change the world of architecture in a far more significant way than Las Vegas ever could. My view then, my prediction, as it were, is that 2022, and especially the first half of 2022, is going to be as it were, the Sputnik moment for architecture, when we can see precisely the capabilities of this thing. And the fact that these things are also generated to think about the environment is part of that whole sort of process. So thank you for listening. That's my presentation for today. Thanks.
Sandra, you want to start? Thank you, Neil, for your presentation. Great summary of all what's going on. I don't know if Sandra, you want to go ahead with your question?
Sure.
Or... Yeah.
Sure. I was unmuted, I'm sorry. Thank you so much, Neil, for a very interesting presentation. And we would like to open up now a moderated discussion and followed by questions and answers from the audience. So it seems that all projects have been discussing the role of data in the analysis and generation of environments. And this has opened radical new ways to perceive our environment and also to generate those environments. So this massive amount of data also requests new techniques and technologies, namely found in AI technologies, as established software just does not allow to work with the new available important information. And the questions are, how does it impact the way we work when we move from expert systems to learning systems? And what do we learn developing these new routines, and what does the data reveal? What criteria are the most pertinent when integrating new techniques and technologies? When you're asking yourself, you have to gather some data from the environment, which is the most pertinent to architecture. And I think here, Neil, probably we could open a discussion of, is it really so that the architect is not necessary anymore, or does the architect just, the role of the architect and the job architect of the architect just becomes more like a gardener who is starting to sustain data and giving the correct and I mean, data will never be unbiased, but the least biased in at least provide data that is biased in a good way.
Well, first of all, I think that much of the research that's gone into looking at the way in which looking at whether AI will take over the jobs of human beings has made the mistake of just comparing one for one AI to human intelligence, because really what's happening is that that AI is being used as a kind of prosthesis, as a form of extended intelligence. I mean, Elon Musk has made the comment that we're all superhuman because of what we can do now with our devices and so on. And the point is, it's not so much one for one, but how maybe one person with the use of AI can do the job of 5 people normally. And this is precisely the kind of the comment that Wan Yu He is making. She doesn't want to let on to all this. I think secretly she knows what's happening, that it's really, and someone's got to do it. Someone's got to produce this AI software. What's going to happen to begin with is effectively that it's going to be very convenient. We're going to be able to use these things. A one-person office will be able to design a huge project, and it's going to be an incredible asset. But eventually, I think that the market's going to creep in, and the clients are going to be wanting to save costs. They're also going to be wanting to guarantee their investment. And at a certain point, you've got to ask, well, what is it going to lead to? And as AI becomes capable, it's not just simply strategically capable. And I think that's the point right now. It's able to work out urban planning proposals, but it has this ability to actually pick up on our aesthetic interests and so on, and to eventually completely autonomously be able to design buildings. That's going to be the real challenge. So to my mind, the other model alongside AlphaGo that we should be thinking about is the self-driving car, because once a car doesn't need is self-driving, you don't need a driver, and once potentially AI becomes so capable that you could design without an architect, you don't need an architect. I actually gave a paper about this in December at the Bartlett, and I called it Squid Games, partly because AlphaGo is Korean, right, and Squid Game is Korean. And I guess the point about Squid Game is that actually, in the end, there is still one person surviving in the game. Not everybody dies. And I think that's probably going to be the case eventually, even when AI is very capable, because you'll find that certain people will demand the personal touch, as it were. Just as right now we have Teslas, we have effectively self-driving cars, people still rent a horse and carriage for a wedding or for a funeral. I think in the future that some will still be kind of like commissioning Zaha Hadid and the Starchitects, not because it's going to be cheaper, it's going to be much more expensive, but a bit like buying a Prada handbag or something. You don't do it to save money, you do it to show that you're not concerned about it. So I don't think all architects are going to die off, but it's going to have a radical impact on our profession. And my point is really for educators, all of us teaching right now, is that we should be aware of that, because we're teaching students who are going to be at the peak of their career when precisely this will kick in. And to my mind, what we need to design are not buildings, but a future for architecture to try and find out how we can survive in this situation. So yeah, that'd be my view.
Thank you, Neil. I don't know if any of the other panelists want to give some feedback, but I was thinking in relationship to the presentations by Maider based on survey and how to think about the environment. Evangelos' presentation in terms of collective emergent behaviors relative to cycles of computation, and Hannah's presentation in terms of material logic and emergence. How can we think, because Neil, you also presented something that to me is very interesting, which is the shift, the Copernican shift in terms of anthropocentric, right, to a different type of reference system, and that entails not only a problem of power, control, and interest, but also a collective, different type of collective intelligence, different type of collective ethics. I wonder, in relationship to that and the presentations of the panelists, how can we think the relationship between big corporate powers? Like, for instance, the worry to me is not so much AI taking over, but the worry to me is the digital feudalism that we're living in today, relative to creating systems to actually make more profit for certain type of individuals, as opposed to a logic that perhaps we are all pushing for, which is a collective effort and collective interest, even beyond human interest. So I don't know if anybody would like to comment on these issues.
I would like to maybe start. First of all, I appreciate a lot the rest of the presentations, and I really like the provocative style of Neil. I would like to take the devil's advocate, and I don't believe that like architects will vanish. Just as long as we retain our synthetic mind or aspect, I don't think we're anywhere near of being eliminated by AI. But to Neil's point, I really believe that as educators, and I have been part of it, not really nowadays, but we should be really pointing towards these things and very rigorously from a conceptual perspective, from a technical perspective, and from a ethical or cultural perspective. So what do these tools mean, and what we can do with that? Now, to the point, just to reframe AI, in my head, maybe, and maybe that's too far off, but let's say we're living the second renaissance of AI. So the first renaissance was like in the 70s. And then AI at that point was promising a lot. It will change the world, will bring so much, like a lot of things happen and rapid research happened because a lot of money went into research, but then it died. So that might happen in 5 years, where people now, the last 3 years, everybody's talking about AI. And yes, they are becoming more competent, but in my understanding, at least from the technical perspective, the most important advancements or achievements like the Go, they rely on a very laborious manual task of training this AI, and some human mind or 30 minds are working together. So in the case of the AlphaGo, yes, the guy lost, but he lost to a machine that was being trained by 30 engineers for some years. And we need to always kind of put that out there. The same, and I will close with that, the same thing happened in the 2000s when we had like digital design parametrics coming in. And it's going to automate design, and we're not going to be having people drafting. And here we are, 2022, and this has become a commodity. People use it, but I don't know how much it has worsened the working conditions of architects. Now, for people that they didn't want to go with that and they didn't want to learn it, and they believe that drawing will never be surpassed, yes, maybe it became a problem. The same thing now with people using maybe parametrics and say, no, AI is not the case. I really believe in these technologies, but I really believe that in architecture, especially, you know, things, and in AC, things take time. And as I said earlier, and I want to close it with that, yes, tools have become accessible, tools have become easy to use, but learning the tool, understanding the principle and doing something useful with it hasn't become any faster. So yes, we can use style guns to generate stuff, but it was the same thing as we were using other computational techniques earlier. They look differently and they have other capabilities, but I don't want to paint the picture black, but I want to side with Neil that this has to be on the agenda of every educator. Like, we cannot be teaching people that this is out there. This is now, and this is happening, and we should learn as architects to think with that.
Could I respond to that just quickly? No, thanks for that comment. I mean, okay, so maybe another year that was really important was 2006. That was the 50th anniversary of the initial Dartmouth summer school, where they launched the term artificial intelligence. And in 2006, they got back together, those surviving, and they realized they hadn't done anything. They'd achieved nothing. We'd had these AI winters and so on. But 2006 was also the kind of revolution of deep learning that has totally transformed the field. And I think we're in a very different situation in the sense that there are a number of factors that are changing things right now. The sheer amount of data that's out there, the better algorithms, the use of cloud computing, and any number of other things, the competition that's going on, the number of people using AI and so on. We're in a different situation. I doubt very much there's going to be another AI winter. So an AI winter was when there was a kind of collapse of confidence because of some of the claims made about AI were not being realized, and therefore whatever. I don't think we're going to find that situation right now. And I think the point that Wan Yu makes is that the key thing was that AlphaGo 0 taught itself without even being given the rules of Go, and that is really astonishing. That takes you into a different sort of world. So I think we're fundamentally in a different situation. One of the comments that came up on last Sunday when we had Jeff Hawkins talking on our AI neuroscience and architecture session, and by the way, Wan Yu will be presenting this Sunday, so I really recommend everyone to watch her, what she has to say herself. But one of the comments that Jeff Hawkins makes is, AI will never be able to compete with the human intelligence. Well, I took a very different sort of view, and what I would say is that the problem that AI has right now in terms of human beings, it doesn't have consciousness. It doesn't know it's playing Go. It doesn't know it's playing chess. It's got no more capacity to think than your pocket calculator. But frankly, we don't need consciousness. This is a comment that Yuval Harari makes that says there are many routes to superintelligence, and not all of them go through the straits of consciousness. Do we need an AI system to be conscious when it's generating the designs such as we're going to see? And I just say this just very briefly. I wish I could show you this final project. I was gobsmacked. I was completely blown away by it. And I can't see it, but we will see it in 2 weeks' time or so. I don't know when. And they will see the potential of that. So we've got to be realistic about it. And I don't think necessarily the lessons of the past in terms of AI winters wants to go by. I think we're now firmly in the age of AI, and there's going to be no more winters. And the way that things are speeding up in terms of Moore's law, of the law of returning, I forget the term that Ray Kurzweil uses now, it's speeding up. Every single publication that we produced is completely out of date by the time we produce it. And the world is changing on a daily basis, and I don't see there's going to be any return, personally.
Yeah, Hannah, go ahead.
Yeah, if I'm correct about the debate whether AI would take over the role of architects or not, I doubt for many reasons, because if we are saying that AI took over the decision-making and making way better designs and so on, I would agree on that, in case we already know the kind of inputs and data we're putting for the decision-making. But since we know that there are so many obstacles and problems that we're facing in architecture, way more than the factors that is already given. That means that, for instance, if we take the resources as a problem, or the current status of the construction and how it goes on, and the real difficulties we're facing into covering this big gap between the design like environment and what's going on computers and what's really currently taking place on site, and how to uncover the problems that is already existing. So the AI is a tool, and it's better to use it, of course, to cover the problems that we already know its inputs. But there are so many unknowns and so many complex problems already existing that we still need to work on, not only architects, but other disciplines. And we need to figure out how to cover this difference or different kinds of data that we are to find a means to contribute to one another and find inputs and outputs. AI could help in that, definitely, but there are so many things that we need to find data for in order to activate this so-called AI, to help us to find problems to existing, to find solutions to existing problems. And there are so much. So it depends. What are we talking about? What kind of context? Is it only the smaller side of the problem, which is getting new forms, getting inside data of building physics, lighting systems, I don't know, different kinds of facade elements, and whatever kinds of geometries we're talking about, that is still controllable. But the problems we're facing in architecture are way, way larger than this. And it needs a lot of data that is still not existing.
I don't want to hog the conversation. Could I respond to that? I think it's precisely that area of the unknown knowns, or the unknown unknowns. What we don't know is precisely where AI is going to come in, and it's precisely. I mean, the Wanyu project was really about environmental control system. Then that logic ran throughout the project, and I didn't talk about it enough, and she will on Sunday, I'm sure. But if you just think about the way that we're beginning to rely on AI for various things, like it's spell check, little things like that, it's finishing our sentence offers and so on, you can just see the potential of what it's going to lead to eventually, and risk management of pointing out where the mistakes are being made. And I think it's precisely that area that it's going to draw attention to. All I would say is that, the example I always give when I'm talking about these things is, when I was a student, at the University of Cambridge, I would go on a trip somewhere. I'd go to a travel agent and I'd get my ticket. I'd queue up and talk to someone about it. And then I'd go to a camera shop and buy reels of film, and I would take them on a holiday. We'd come back and then I would get the films developed. None of that happens anymore. We all book online. There are some travel agents, but they've almost totally died out. They don't even have camera shops very much these days, because we all have this cameras on our phone, and we certainly don't develop our camera reels. So let's not assume that because they were there in the first place, that it's going to be like that in the future. Let's go back to the comment that Henry Ford made. Was if I asked people what they wanted, they would say, I want to have faster horses. And in fact, the car came along, right? And as a result of that, all those horses became unemployed. So let's be realistic about this and not cling to these kind of sentimental versions of the world from the past, and really engage with the present and begin to predict about the future. My concern about architecture, frankly, as a discipline, we spend all our time looking back at the past, all the time looking back at Alberti or something, right? No. One point that I want to make, I translated Alberti, right? Alberti was a revolutionary, right? He was an absolute revolutionary. He changed the world of architecture, right? And I just want to finish off the final sentence of my book about the dark side of things is going to say, well, actually, he gave us a definition of the architect to the present. And unfortunately, AI is going to take over. And by a strange irony, the name Alberti begins in A and ends in I.
The problem that I see, I actually agree with the conversation, and I think that one of the issues is the cultural role of architecture that I think is being displaced. And I think that one of the notions that at least I'm more interested in, and I'm actually studying and developing projects, which is a little bit what Evangelos you presented, which is the computational environment as a self-regulating agency, which is that we have different types of AI, different type of neural networks. And to me, the most interesting advances are the ones that are actually self-emergent organizational structures for the flow of information. And in that sense, to me, the current barrier that I see in AI is that the technology is being normalized as if it is mainstream, when in reality there are different theories, different histories about what AI is and what different ways of channeling information. The problem, Neil, about not looking into the past is that all what we are working with AI is based on past information, because we're flowing data, and AI systems are robust since 2013, mainly because of the amount of data that we're able to load in. Now, all that data, as you correctly say, and I agree with you, is full of biases, and we need to look forward to the future. Now, the contradiction resides there, that AI systems are strong because of past data, and the anticipatory road is becoming so biased because of that, right? So I think until we resolve a dynamic self-organizing system that actually takes that into account, I think architectural culture is still going to be a kind of limitation that AI may have to deal with, or at least we have to surpass the origination of that data in relationship to the structure of how that data is being processed. But I don't know if anybody would like to address, because one of the interests why I'm interested in survey is exactly of that, the mechanism of recording of existing information relative to how we project to the future. And I think that the AI current limitation is that, for instance, to me, the contradiction of Kopp Himmelblau's project is that you're using the repository to create something that's supposed to be new, is culturally totally retrograde in relationship to the technology implemented. And that's my criticism of using repositories, and perhaps not think about the repository as a project in itself from a cultural point of view.
Yeah, I agree with that actually. I mean, I do agree with Neil that the transformation in the discipline is happening, and it's going to become evident in the next few years. But also with what Pablo just said, because AIs are built with some sort of logics of standards. You know, we train the AIs based on what we consider to be good data. We don't really know what good data is, or I mean, data is, as Sandra mentioned, is always biased. Data that is validated, no, what this means, it's, you know, again, we are adding uncertainty. So this logic of standards and training with good data is leading towards, you know, an output that should be building on what we did before, because that is what we considered validated, ticked, so on. So this kind of notion of creating something novel that is going to engage with, you know, other cultural biodiverse practices, or, you know, this kind of notion of novelty or newness, I don't see it happening in the very near future. I know that we are going to go much farther, you know. I'm talking about immediate, you know, years. I don't see the AI processes getting us there. So I don't see a replacement of the architect as of tomorrow. That may happen eventually, but not as you know, as the way AI engages with complex system management through a standardization.
Tom has a question in relationship to what Maider just said and what Neil was saying. Tom, you want to express your question because it's related to the architect?
Yeah, sure. Thank you. No, as I've written it, Neil Leach, you've articulated very clearly the risks of the death of the architect, and you've proclaimed that. And of course, there's a great excitement about the use of AI to chart new directions for architecture, which is, you know, substantiated and evident by this panel on the subject. The question is the panel alarmed by the use of AI, for example, in facial recognition, surveillance systems, control systems, in cities, or on the scale of urbanism, or on a planetary scale, which can be summarized by a sort of banner taxonomy that we call the smart city?
Can I respond to that, Tom?
Sure.
Yeah, I think there's a great risk in what I would call technological determinism, and that is assigning a certain sort of use to a technology and thinking that it's going to inevitably lead to that. And I think that's where I get very worried about these books like Atlas of AI, or indeed Surveillance Capitalism, is that they seem to assume that, you know, in the end, you know, a tool has certain affordances and you can use it for certain things, but it's up to the person and who that uses it. So a kitchen knife you can use to cut up your vegetables, or you can murder someone with it. AI facial recognition can be used for totally benign purposes, like on a phone. It opens up your phone, or it can be used in a very negative way. And I think that those working in the field of AI are very alert to that. There is I don't know if you know that little movie that was put together, and I'm forgetting the name of the person who did it now, but one of the great authorities on AI, a movie called Slaughterbots, where they were basically looking at how AI was going to be used in the battlefield. And frankly, I'm quite surprised we haven't seen more AI being used in the last few days in Ukraine than we have, because this is the first war in the age of artificial intelligence. But no, I think one has to be alert to that. But in the end, don't blame the technology. You know, we have an expression in England: a bad workman blames the tools. I think a bad theorist blames the tools. I think one has to be more open-minded.
So yeah, so no, I partially agree and partially disagree, but doesn't matter, because I think that media determinism is perhaps something different, because in a way, the question is the cultural bias through which the technology is not only producing a certain structure, but also producing a certain way of determining reality through measurement, through standardization, through the same structure of how data is actually being processed. So I think I don't think that we're talking any longer about the tool anymore. I think that we are talking more about an ecosystem, because a tool doesn't really have feedback. And I think in AI, the old issue of feedback now with reinforced deep learning goes beyond just a regular kind of automated feedback, but it's actually much more complex. So I think that in that sense, the relationship between the data fed, the data weighting, I mean, we didn't talk about data science because data science is another issue as well, right? But the relation between data science and computer science, they're both moving, right? And they both have different kind of projects. Even mathematics has a different version of what we are actually doing. So I think that in a way, perhaps this is for another conversation to get deeper into the subject and to analyze the different types of AI and the different types of intelligence that are emerging. And I agree with you, Neil, that you mentioned that why do we need actually to replace humans? I totally agree with that. I think that we are in an emergence of a different type of intelligence, and we don't need to actually claim back the cybernetic approach. I think that we are facing a different type of emergent systems, and I like the way that the panelists, they all kind of reinforce that in their own different projects and their own different cultural projects that they presented today. So I thank everybody. I don't know, Sandra, if you want to say any final words, but we are beyond our time already, but I let you close the event.
Well, thank you so much, Pablo. I just wanted to thank the great panel and congratulations to the amazing work we have seen and that is being presented today. It was really a special, especially interesting to share these projects, and we're looking forward for the future lectures in the series. Thank you so much, Pablo, for organizing and for doing this. Thank you to the organizers. Thank you to Susan, who did a great job in establishing everything. And thank you for the audience to come to view this series.
Thank you, everybody. Thank you, Hannah, Evangelos, Neil, and Maider. Thank you for participating.
Thank you for the
Thank you,
invitation.
everybody.
Great talk.
Take care.